In this video, I'm going to review some stoichiometry problems involving gases. I highly recommend you watch my video on stoichiometry problems first before you go into this one. Some things we're going to keep in mind is first off the ideal gas law. We're going to be using that and the constant in the ideal gas law, the basic constant, which involves liters, atmospheres, moles, and Kelvin. Standard temperature and pressure, which is 0 degrees Celsius or 273.15 degrees Kelvin. That's 1 atmosphere, or about 1 atmosphere. 1 atmosphere is also equal to 760 millimeters of mercury, 760 torr. And we're also going to use the fact that for every 1 mole of any substance, you have 22.4 liters of that substance. So you can use that as a conversion between moles of a substance and volumes of a substance, or vice versa. So we'll be using that too. Because again, we're dealing with gases. So the first problem, we're given a mass of H2, and we're told it's in this container, this certain size container at this temperature, and they're saying what's the pressure, and specifically in millimeters of mercury. So really, we just have to find the pressure. That's the main thing. So let's look at what we're given. We're given a mass. We're also given the volume. We're given temperature. (20°C), and they're looking for pressure. And any type of gas problem, I always think, can I use PV equals nRT? That's always the first thing that jumps in my head. So in this problem, I can see that I'm given volume. All right, awesome. I'm given temperature. Great. This is a constant, so R. I always have R. And they're looking for pressure. So the question is, can I find moles? So I can plug all these other things in to find pressure. And yeah, you're given a mass. All you gotta do is convert the mass to moles. So we'll do that, and then we can plug everything in. Before I do that, let's convert this to Kelvin first, because that's really easy. Okay, so we have the temperature in Kelvin. So yeah, I can plug all that in. I just need to find the amount of convert the mass to moles, and then I'll be able to do this problem. I'll be able to plug it all into the ideal gas law. So I got my grams of H2, and I need to convert that to moles of H2 and get rid of that grams. So for every 1 mole of H2, it's just about 2, so it's going to be about 1/2. Not too bad. Now I can plug all this in to the ideal gas law. So I'm trying to find P. My volume is just 2. My amount of moles is about 1/2. The ideal gas law constant, or the gas constant for this law, you can look it up, and we had it on the previous slide. Again, keep in mind that's in atmospheres per liter by moles and Kelvin. So our answer is going to be, we're going to see in a second, it's going to be in atmospheres. And we calculated the right temperature to plug in there. So pretty easy math to do here. Then you divide each side. So P comes out to about 6.5. And again, this is in atmospheres, because this guy right here was in ATM. So this gives us our answer in atmospheres. The question asks for the answer in milligrams of mercury, or excuse me, millimeters of mercury. So I have to convert that really quick. To convert that, you just basically, we're going from atmospheres to millimeters of mercury. Trying to get rid of atmospheres. For every 1 atmosphere, you have 760 millimeters of mercury. So your final answer comes out to 7 millimeters of mercury. So overall, not too bad of a problem, considering that you just got to plug this stuff into the ideal gas law first, converting mass to moles. Next problem, really straightforward, looks really simple, and there's two ways we're going to do this one. First, we're going to do this problem just like we did the last one, and I'm going to show you an optional, a different way of doing it that's really useful. It's actually a lot more simple. So first, in setup like we did before, so we have a volume, or they're asking us for volume, and they're giving us a mass. So the mass of this argon they give us here is 20 grams of argon. And they tell us it's at standard temperature and pressure, which is it's like set value. So whenever you see STP, it actually makes things a lot easier. So our volume, we don't know, we're going to find that. The temperature is just standard, so it's 0 degrees Celsius, which is just 273 Kelvin. And our pressure is just standard, just 1 atmosphere. So again, whenever I see problems like this, I just think, can I use PV equals nRT? So I got the temperature constant. In this case, we're looking for volume. They give us pressure, and again, same thing. I can calculate the moles, the amount of moles. I just got to convert grams to moles. That's it. So let's do 20 grams of argon, and we'll get that to moles of argon. For every 1 mole of argon, if you look at the periodic table, the mass of argon is just 39.9. Again, that's about 1/2 for moles of argon. And now we have our mole values, so we can just plug in all the numbers, and then we can solve for V. So when you plug them all in, it's just 1 times V is equal to 1/2. That's our N. Constant is always the same. 206 times the temperature, just standard. And we do the math for this guy, it's just 11.2 liters. So that's the volume. So this is one way to do it. There's another way to do it, which is a lot easier. And it takes the fact that we had a conversion, going back to previous slides here. If you go back to the very first slide we started out with, that conversion factor of, for every 1 mole of anything, just anything at all, you have 22.4 liters of that substance. So using that, we can take this number right here and convert the moles right into liters. So when we calculate that we have about 1/2 mole of argon, we can say, well, if you just want to convert that to liters and you want to get rid of the moles, well, for every 1 mole, you have 22.4 liters. So 1/2 of 22.4, that's 11.2 liters of argon. And you can see it's the same as the answer we just calculated using the ideal gas law. What's useful about this is as you practice more and more chemistry, you can do problems like this just in your head when you look at, okay, I have about 1/2 mole, I want to get volume, about 1/2 of 22.4, that's 11.2. And you can easily go through questions like these and move on. Let's do one more. Last one. So here they're asking us how many liters of water can be made from 55 grams of oxygen gas. Problem with this question here, right off the bat, is I'm seeing that they're giving me one thing and they're asking me for another thing. They're giving me oxygen gas and they're asking for amount of water. So obviously a reaction occurred. That tells me a reaction occurred. So it would be tricky to use PV equals nRT. I don't even know if I can. So I'm probably going to have to just do some unit conversions here, a bunch of unit conversions. And I'm definitely going to have to write out this reaction. So they're telling me I have a reaction between oxygen and hydrogen, which is just to make water. Easy. So when in this reaction, they give me an exact amount of O2. They give me plenty of H2, more than enough, it's excess. And they're saying how much water are you going to make with this specific amount of oxygen. So you have 55 grams of oxygen. And again, I can't really think PV equals nRT here. I'm thinking unit conversions, just like you would do most of the time in stoichiometry. You're doing a bunch of unit conversions. So this is a real stoichiometry problem involving gases, whereas the previous two were more, you could use PV equals nRT. So 55 grams of O2. And they're saying how much water am I going to get? So the first thing I'm thinking is I'm given a mass. I want to convert that to moles of the O2. Then I'm going to convert it to moles of water. That's what they're asking. And then they're asking me for liters. That's a volume. So then I got to convert it to a volume of water. So I get 55. Let me convert to moles of O2. For every 1 mole of O2, I have 32 grams of O2. So that converts from grams to moles. After converting from grams to moles, I want to convert from moles of O2 to moles of water. So moles of O2 are going to cancel out, and I'll get my moles of water. As you can see in the reaction, for every 2 moles of O2, you have 1 mole. Excuse me, for every 1 mole of O2, you have 2 moles of water. I want water, so I put that on top. I'm going to get rid of the O2, so that will cancel out. So I'm at this step right now. Last step is converting the moles to liters. And here I'm just going to, again, I want to put liters on top, moles of H2 on the bottom, so it cancels out. For every 1 mole of anything, you just have 22.4 liters of that substance. And this is my setup right here. That's it. That gives me my answers in liters of water. So it's just 55 divided by 32 times 2 times 22.4. And that will give me 77 liters of H2O.